You ever stop and wonder what a thought actually is? You know, how does your brain tell your hand to reach for a cup of coffee? Well, today we are going on a journey deep inside your head. We're going to uncover the incredible biological machinery that powers every single thing you think, feel, and do. And our first stop? It's the one big idea that makes this whole thing possible.
This one powerful idea is the foundation for everything we're talking about today. It means that every feeling, every memory, every choice you make, it's not just happening in some abstract mind. Nope, it's a real, physical, biological event happening inside your body, right this very second. So what's the takeaway here? It means that to really understand ourselves, we kind of have to understand the hardware we're running on. And that is exactly what we're about to do. We're going to trace the path of a single message as it zips through your body's amazing communication network. All right, first things first, we need to meet the hero of our story, the fundamental building block of your entire nervous system, and that is the neuron. It's just a tiny little nerve cell, but wow, is it the most important information processor you've got?
And the scale we're talking about here is, well, it's just mind-boggling. Your brain is packed with about 100 billion of these little messengers. To put that in perspective, a piece of your brain the size of a single grain of sand holds around 100,000 neurons. Just incredible.
So let's zoom way in and look at just one of these messengers. You know, at first glance, it kind of looks like a weird little tree, right? With roots and a trunk and some branches. But believe me, each one of these parts has a very specific and absolutely crucial job to do.
First up, we've got the dendrites. You can think of these little branching fibers as the neuron's ears, or maybe its antennas. Their entire job is to listen, to receive all the incoming messages from thousands of other cells around them.
Okay, so once the neuron has listened to all the messages and decides it's time to talk, it sends its own message down this long fiber, the axon. So if the dendrites are the listeners, the axon is the speaker. Its job is to carry that signal away from the cell and onto its final destination. Now, many axons have this special fatty coating called the myelin sheath, which is just a brilliant piece of biological engineering. It works exactly like the plastic coating on an electrical wire. It insulates the axon, which allows the electrical signal to travel ridiculously fast. In some cases, we're talking over 250 miles per hour.
Okay, this next part is super important. It's the golden rule for our entire journey today. Communication happening inside a single neuron is an electrical process. But when it's time to pass that message to the next neuron in line, it switches. It becomes a chemical signal. Let's break down both of those parts.
First up, let's look at the electrical part of the story. This is the high-speed relay race happening inside every single one of your billions of neurons all the time.
This electrical message is called an action potential. Really, it's just a brief, powerful zap of electricity that shoots down the axon. And here's the thing, neurons follow an all or none law. That means they either fire at their absolute full strength or they don't fire at all. There is no in between. It's like a light switch. It's either on or it's off. So how is this little electrical charge even created? Well, it's through some really clever chemistry. The surface of the neuron acts like a gatekeeper. And when it's time to fire, it opens the gates and lets these electrically charged particles called ions flood in. This super fast exchange creates a pulse of electrical energy that moves down the axon like a tiny spark. Honestly, the best way to picture this is to think about the wave at a big sports stadium. You know how the wave itself travels all the way around the arena, but each person just stands up and sits back down? It's the exact same idea here. The action potential, the message, flows all the way down the axon, but the individual ions just move in and out right where they are. So our electrical impulse has raced to the very end of the axon, but now it's hit a roadblock. There's a gap. The next neuron is just across the way, and to get there, the message has to completely change its form. See, the end of the axon doesn't actually touch the next neuron. There's this microscopic gap between them. We're talking less than a millionth of an inch wide, called the synapse. And this tiny little space is where the real magic happens. This is where the electrical signal gets converted into something else. To cross that gap, the sending neuron releases these special chemical messengers called neurotransmitters. Think of them like tiny little couriers. They float across the synapse and then fit into receptors on the other side, just like a key fitting into a lock. And that unlocking
is what tells the receiving neuron whether it should fire off its own message or just stay quiet.
But what about all the leftover neurotransmitters floating around? Well, the system has this incredibly efficient cleanup crew. In a process called reuptake, the original neuron that sent the message actually sucks the extra chemicals back up. It recycles them so they're ready for the very next message. So smart. Nothing goes to waste.
Okay, so now that we've seen how two neurons talk to each other, let's zoom out. Let's see how these billions and billions of tiny conversations come together to create your body's entire information superhighway, the nervous system.
So your nervous system is basically split into two main parts. First, you have the big boss, the command center, the central nervous system, or CNS. That's your brain and your spinal cord. Then, branching out from there, you have the peripheral nervous system, or PNS. These are all the nerves that go out, gather information, and then carry out the orders to the rest of your body. Now, the PNS itself splits into two more categories: the somatic system, for things you control, like waving your hand, and the autonomic system, for all the automatic stuff, like your heartbeat.
And that automatic or autonomic system has these two competing divisions that are always working to keep your body in balance. You've got the sympathetic division, that's your fight or flight response. It's what revs you up and gets you ready for action. And then you have its partner, the parasympathetic division. That's your rest and digest system. It's the one that calms you down and saves energy once the coast is clear. One hits the gas, the other hits the brakes.
Phew, okay, let's put it all together now. We've looked at all the individual parts, and now we get to see how they all work together in perfect harmony. Let's trace one single message from the very beginning to the very end.
So here's the entire chain of events. It all starts with some kind of input signal at the dendrites. That triggers an electrical fire, the action potential, that shoots down the axon. Then you get the chemical handoff with neurotransmitters hopping across the synapse. And finally, that activates the next neuron in the line, which starts the whole process over again. And you have to remember, this entire four-step journey happens billions of times every single second to create every single thought you have and every action you take.
So, we've traveled from a single electrical spark all the way to the body's entire superhighway, but we've really only just scratched the surface. And it leaves us with this final, fascinating paradox. The very organ we're using right now to try and understand all this is itself the most complex thing we have ever discovered in the universe. Something to think about.